There are three things you need to know how to do with an alternating series: test for convergence, test for absolute or conditional convergence, and find the error. To test for convergence, find the limit as n approaches infinity of the function a sub n. If it's 0, then the series converges. For example, if you were asked to determine the convergence of this series, you would take the limit as n approaches infinity of a sub n, or n over 2n squared, plus 3n plus 1. You might have to use L'Hopital's rule or divide by the highest power in the denominator. So, since the limit as n approaches infinity is 0, the series converges by AST. Remember that AST can only be applied if the function a sub n is positive, continuous, and decreasing. You should always justify your answers, but remember that AST only proves convergence. If it diverges by the divergence test. The most common way alternating series will show up on the AP test is when you're asked to test the endpoints of an interval of convergence. Say you're given the Maclaurin series for a function f of x. After applying your ratio test, you find that the interval of convergence is between 1/2 and -1/2. So now you test your endpoints. When x equals -1/2, the series becomes -1 to the n plus 1 over n plus 1. Applying AST, we find the limit as n approaches infinity. So, the series converges by AST at x equals -1/2. Whenever you see a series with a -1 to the n or a -1 to the n plus 1, you know you're either going to use the alternating series test, the root test, or the ratio test. But you also might get an alternating series with a trig function. If you have cosine of n pi over n squared, you can apply AST because cosine of n pi oscillates between 1 and -1. N equals 0 gets you 1, n equals 1 gets you -1, and so on. Next, we test to see if the series is absolutely convergent or conditionally convergent. If a series is absolutely convergent, it would converge even if it did not alternate, whereas if a series is conditionally convergent, it converges only because it alternates. To determine if a series is conditionally or absolutely convergent, determine if the series of a sub n converges. Using our previous series, we determined the convergence of n over 2n squared plus 3n plus 1. N over 2n squared plus 3n plus 1 is less than n over 2n squared, which is equivalent to 1/2 times 1 over n. 1 over n diverges by p-series, which means that n over 2n squared plus 3n plus 1 diverges by direct comparison test. And since this converges, your alternating series is conditionally convergent. Moving on to error. The error for an alternating series is given by r sub n is less than or equal to a sub n plus 1. In other words, the error at any term n is less than or equal to the next term. With alternating series error, you could be asked one of three questions: S sub n, or the sum of a series up to a certain term, approximating the sum within a certain value, and how many terms are needed to approximate the sum within a certain value. To find S sub n, just plug it into the series. If you want to find S sub 6, plug in n's until you get to n equals 5. Okay, ignore that last part. Plug in n until you get to n equals 6. If you add all of this up, And on the graphing calculator, you get 0.122. The error for s sub 6, or remainder, is less than or equal to the next term. And the next term is 7 over 6 to the 7th. So the error is going to be within 7 over 6 to the 7th, or 0.000025. If this question had asked you to approximate the sum within an error of 0.000025, then s sub 6 would be your answer. If it had asked you how many terms were needed to approximate a sum within this error, then 6 terms would be your answer. To approximate the sum within a certain value, you can write out all the terms as we just did, find the term that is less than or equal to your error value, and add up all the terms before it. But writing out the series can take a long time, so I wouldn't recommend this unless you have the series already written out. Instead, you can use algebra. For example, if you're asked to approximate this series within 0.001, then you want to find the n value that gives us the error within 0.001. Some n value must be less than or equal to your desired error. The negative 1 goes away because in the formula there are absolute value signs. Forgot the factorial. Sometimes it works out nicely and you can find n just by using the solve function in your calculator, but this time we have to do some guess and check. And you're plugging the n's into this function. The fifth term is less than or equal to the given error, so the sum of the terms before, n equals 4, approximate the sum. Now if you were asked how many terms would give you the given approximation, you would stop here, and your answer would be n equals 4. Since we're asked to approximate the sum, we need to find s sub 4, which equals and we're getting all of these terms from our original series. And the answer is 0.041. How many terms are needed to approximate this sum within 0.0001? As before, we need to find some value n that is less than or equal to the given error. This one can be solved on your graphing calculator. After you plug everything in, you get that n equals 3.788. If you have a decimal, you're going to round down because the fourth term will give you the error that you need. Therefore, you only need the sum of the first 3. So your answer will be 3 terms. In alternating series, you always round down.